There's a machine sitting in your kitchen right now that has not fundamentally changed in almost 200 years. An American invented it, and a research team working in Maryland may have just built the thing that finally ends its long run, using nothing more complicated than a metal tube and a controlled squeeze. Almost nobody knows the full origin story. The refrigerator was not invented in Europe. It was not invented in China. The first working vapor compression cooling machine was patented in 1834 by a man from Newburyport, Massachusetts, named Jacob Perkins. He built a device that could make ice on demand. In doing so, he handed the modern world reliable food storage, medicine preservation, and livable summers in hot climates. Nearly 2 centuries later, the fridge humming behind you is still running on his core idea: the same trapped gas, the same pumping heart. Every upgrade since has been incremental improvement on a design older than the light bulb. And now the country that started the technology may be the one that replaces it, not with a bigger compressor or a smarter control chip, but with a solid piece of metal that gets cold when you stop squeezing it. If you find stories like this useful, hitting the like button helps more than you might expect. These videos take real research time to put together properly. Subscribe and turn on notifications so you do not miss the next one. The physics behind the new approach is so simple that you have already felt it with your own hands. You just never connected it to refrigeration. Scientists have understood the basic effect since 1805. The problem was never the science. The problem was that every time engineers tried to turn the effect into a practical machine, the machine tore itself apart. That was the wall that stopped progress for decades. A team in the United States has now found a way around it that sounds almost too straightforward to work. Before you can fully appreciate why your current refrigerator may one day look outdated, you need to understand what is actually happening inside it every single day. Think about every cold thing in ordinary life: the kitchen fridge, the window air conditioner, the vents in your car, the freezer wall at the grocery store, the cabinet that keeps vaccines stable at the pharmacy, the cold room behind the restaurant you ate at last week, the ice machine at the hotel, the chill display case at the convenience store. Every one of them runs on the same principle Jacob Perkins introduced almost 2 centuries ago. It is called vapor compression refrigeration, and it is arguably one of the most important inventions people rarely stop to think about. Remove it from modern society and grocery chains would collapse within days, hospitals would lose critical medicines, large parts of the country would become nearly unlivable in the heat of summer. The entire cold chain that keeps food safe from farm to table depends on this one idea. Here's how the system works in plain language. The machine takes a special chemical gas and compresses it hard into a small space using a mechanical pump called a compressor. Compression makes the gas hot. That hot gas is pushed through coils on the back or bottom of the fridge, where the heat escapes into the surrounding room. As the gas loses heat, it condenses into a liquid. Then, the machine lets that liquid expand into a wider space. When it expands, it becomes cold and absorbs heat from the air inside the fridge. That absorbed heat is what makes the interior cold. The cycle repeats continuously, hour after hour, year after year. It is an elegant and reliable system. It also carries 2 problems that have never fully gone away no matter how much the industry has refined it. The first problem is the compressor itself. It is a mechanical device with moving parts, pistons, valves, bearings, that pump thousands of times an hour for years on end. That is the familiar hum or occasional click you hear in the middle of the night. It is also the main reason refrigerators eventually fail. Bearings wear down. Seals, fatigue. Moving parts simply wear out under constant use. There's a small engine running day and night only a few feet from your food, and the day it finally stops is the day the appliance becomes nothing more than an insulated metal box that can no longer keep anything cold. The second problem is more serious and largely invisible to the average person. It is the refrigerant gas sealed inside the pipes and coils. The word sealed is relative. The gas can slowly seep at joints, escape during routine service, and especially leak when the unit is eventually discarded or recycled. Some of these chemicals are extremely powerful greenhouse gases. One of the most widely used refrigerants of recent decades has a global warming potential roughly 1,400 times that of ordinary carbon dioxide. A single pound of that gas does the climate work of more than 1,000 pounds of exhaust from a car. Multiply that figure by every refrigerator, freezer, car air conditioner, supermarket display case, and commercial rooftop chiller in the country, and the total impact becomes enormous. The United States has already acted on this reality. Under the AIM Act, passed in 2020, the country committed to phasing down these high-warming refrigerants by 85% over a 15-year period. The law is on the books. The deadline exists. Yet the leading substitute chemicals now being introduced are either flammable, operate at significantly higher pressure, or break down into other compounds that regulators are already watching carefully. America has essentially legislated itself into a difficult corner. It has promised to stop using the working fluid that the entire cold chain depends on without yet having a fully clean, safe, drop-in replacement that works in every existing system. That uncomfortable situation forced researchers to ask a different and more radical question. What if the answer is not a better gas at all? What if the answer is no gas whatsoever? That question sent teams of scientists and engineers back to a physics effect discovered long before the Civil War, an idea that sat in textbooks for generations because no one could turn it into a durable, practical machine. Take a thick rubber band. Stretch it quickly and firmly, then immediately press it against your upper lip. It feels warm. Now let it relax fully back to its original length and press it to your lip again. It feels distinctly cool. You just ran a miniature refrigeration cycle with nothing but your hands. The effect is completely real and very old. An English scientist first described it carefully in 1805. Later, researchers quantified the temperature changes. It is called the elastocaloric effect. The underlying principle is disarmingly simple. When you deform certain materials, you force their internal atomic structure into a more ordered arrangement. Greater order releases heat. When you release the material, the structure returns to a more disordered state and absorbs heat from whatever is touching it. No gas is required. No chemical leak is possible. No continuous compressor is needed. Just a solid material that gets cold when you stop squeezing or stretching it. For more than a century, this remained a laboratory curiosity and a classroom demonstration. A rubber band can move only a tiny amount of heat, and it degrades after a relatively small number of cycles. There was simply no material strong enough and durable enough to survive the tens of millions of cycles a real household refrigerator would demand over a decade or more of continuous use. Then, in 1959, a metallurgist named William Buehler, working at the Naval Ordnance Laboratory in White Oak, Maryland, was trying to develop a better alloy for the nose cone of a Navy missile. He mixed nickel and titanium in carefully controlled proportions. What he produced was a metal that behaved like nothing anyone in the lab had handled before. Bend it, and it snapped back to its original shape. Heat it after deformation, and it returned to the shape it remembered as if the metal itself had a memory. The alloy was named for its place of origin, Nickel Titanium Naval Ordnance Laboratory, shortened to Nitinol. It is a thoroughly American invention, funded by the American Military Research Establishment. Today, Nitinol is used inside heart stents that keep arteries open in millions of patients, inside flexible eyeglass frames, and inside precision actuators in aerospace systems. Its most interesting thermal property, however, was not the one first exploited commercially. When you squeeze nitinol, its crystal structure snaps into a tighter phase, and the metal heats up by tens of degrees. Not a fraction of a degree, but a clear, usable temperature rise. Release the pressure, and the temperature drops just as sharply, pulling heat out of everything around it. That is essentially a rubber band with the mechanical strength of aerospace metal. That is a refrigerant you can literally hold in your hand. The United States Department of Energy took notice of the potential. In a major formal assessment of alternatives to conventional vapor compression cooling, federal analysts ranked elastocaloric cooling near the very top of the list of non-vapor compression technologies that showed real potential to replace the compressor entirely. So, the obvious question is the one most people ask as soon as they hear the story. If the material was invented in 1959 and the government ranked the approach so highly, why is there not already a nitinol-based refrigerator in every kitchen in America? The answer is that for roughly 50 years, every machine anyone tried to build from the material eventually destroyed itself under repeated use. The instinctive and most obvious way to use nitinol is to pull it. Stretch a wire or a thin strip in tension, release it, and harvest the cold that appears. The cooling effect works beautifully for a few thousand cycles. Then the material begins to fail. Any microscopic flaw, any surface roughness, any grain boundary inside the metal becomes a stress concentration under tension. Each pull opens the tiny flaw a little wider. Each release allows it to close slightly. Over repeated cycles, the crack grows until the metal finally shears apart. It is the same reason you can snap an ordinary paper clip, by bending it back and forth many times, even though you could never break it with one single strong pull. Metal often fails from repetition more than from pure force. A kitchen refrigerator must cycle its cooling system continuously for 10 to 15 years of normal household use. That requirement translates into tens of millions of cycles. Early elastocaloric prototypes reached the end of their fatigue life in only weeks of continuous laboratory operation. Researchers would carefully build elegant machines, run them under controlled conditions, and then watch the very component responsible for the cooling develop hairline fractures and fail. There was a second serious barrier right behind the first. Nitinol needs relatively high mechanical stress to trigger its full phase change. Engineers found themselves spending large amounts of energy just to strain the material, and recovering only a fraction of that energy as useful cooling. The efficiency numbers looked disappointing when placed next to a conventional compressor that industry had been optimizing relentlessly for a century and a half. By the 2010s, elastocaloric cooling had acquired a clear reputation inside the research community. Beautiful and elegant physics, but broken and impractical engineering, a technology that could cool a small volume very impressively right up until the moment the active material tore itself apart. That is the point at which a team at the University of Maryland, working in close collaboration with the Department of Energy's National Laboratory System, under materials scientist Ichiro Takeuchi, asked a question so simple it almost sounds like a joke when you first hear it. What if we stop pulling the metal and start squeezing it instead? Cracks grow and propagate under tension. Compression does the opposite. It presses microscopic voids and flaws closed. Squeeze a piece of metal rather than stretch it, and the tiny defects that would normally become fractures are clamped shut on every single cycle. Instead of thin strips or wires pulled apart in tension, the Maryland researchers switched to nitinol tubes and drove them in pure compression along their length, using carefully controlled hydraulic force. The phase change remained the same. The heat was still released on compression and absorbed on release. The fatigue behavior, however, changed radically. The results, first published in the journal Science, shifted the direction of the entire field. The compression-driven system did not merely last longer, it delivered useful cooling power and temperature spans large enough to move the technology out of the category of laboratory curiosity and into the range of devices that could realistically compete with existing systems. Subsequent work through 2025 and into 2026 continued to improve the performance numbers. Higher coefficients of performance, larger achievable temperature differences, successful demonstration of sub-zero cooling with specially formulated alloys, and early experiments with 3D printed nitinol structures that open new possibilities for complex shapes. The physical architecture of the system is itself important. Picture a compact bundle of thin nitinol tubes arranged somewhat like the barrels of a revolver cylinder. A hydraulic driver compresses the entire bundle in a controlled stroke. As the tubes compress, they heat up. A simple closed loop of ordinary water carries that heat away to external coils where it is rejected to the room. Then the driver releases the pressure. The tubes spring back toward their remembered shape, become sharply cold, and the same water loop runs back through them to pick up the cold and deliver it to the compartment that needs to stay cool. Notice carefully what is completely missing from that description. There is no refrigerant gas of any chemical composition. The only fluid moving in the system is ordinary water, the safest and most environmentally benign working fluid available. The only refrigerant is a solid piece of engineered metal that never leaves the sealed machine. If the entire system somehow ruptured in a kitchen, the environmental consequence would be nothing more serious than a puddle of water. Notice something else of practical importance. A conventional compressor must run more or less continuously. The moment it stops, the pressures equalize and cooling ends. An elastic-caloric core can be driven in discrete mechanical strokes matched precisely to the actual cooling demand at any moment. It is fundamentally quieter because there is no continuous pulsing mass of compressed gas, only a controlled mechanical squeeze followed by a release. And when the unit finally reaches the end of its long service life, the active material itself is recyclable nickel and titanium that can return directly into the industrial supply chain rather than a regulated chemical that must be carefully recovered by trained technicians. The Maryland team and the research groups that followed their lead quickly realized they had built something more general than a better household refrigerator. They had built a platform technology for moving heat at almost any scale. That realization arrived at a moment when several critical sectors of the American economy were facing exactly the kinds of cooling problems that traditional vapor compression systems handle poorly or expensively. Large data centers running intensive artificial intelligence workloads consume enormous amounts of electricity, and a substantial share of that power is spent not on the actual computing, but on removing the concentrated heat generated by dense racks of processors. In regions already facing water stress, the evaporative cooling towers used by many facilities have become political and environmental problems as well as engineering ones. Electric vehicle battery packs generate intense heat during fast charging. How well that heat is managed largely determines how many years the expensive battery lasts before its capacity fades. Military submarines require extreme silence. Every vibrating compressor is a potential acoustic signature that can reveal the vessel's location. Spacecraft face the special difficulties of fluid loops and microgravity, and the absolute intolerance of any leak in a closed system far from any repair facility. In all of these cases, a solid-state cooling element that can be scaled from the size of a suitcase down to the size of a deck of cards and placed directly against the source of heat is a far better geometric and practical match than a large remote machine pushing chemical gas through long runs of piping. Vapor compression gave the modern world the reliable cold chain that makes contemporary life possible. Solid-state elastocaloric cooling, if it can be brought to true commercial scale, offers a way to move heat at almost any physical size without depending on a working fluid that environmental regulators are actively trying to phase out of existence. That strategic importance is exactly why the research is now treated as a funded national priority. with parallel efforts running at multiple Department of Energy, national laboratories, and in university spin-out companies working to commercialize the active cores. It is essential to be completely honest about the present stage of development. What exists in laboratories today are advanced prototypes and early pre-commercial demonstration units, impressive and encouraging ones, but not finished products sitting on the floors of appliance stores. There is no publicly announced date when an ordinary consumer will be able to walk into a retail store and buy a fully elasticaloric refrigerator. The remaining obstacles are real, specific, and non-trivial. Nitinol is not a cheap commodity metal. The alloy must be melted under carefully controlled vacuum conditions because titanium reacts aggressively with oxygen in ordinary air. The precise ratio of nickel to titanium must be held to extreme accuracy because a shift of only a fraction of 1% moves the temperature at which the entire phase change occurs. Specialty melting furnaces and a limited number of qualified suppliers are required. A conventional steel or aluminum compressor is a mass-produced commodity stamped and assembled by the tens of millions every year. A precision bundle of nitinol tubes is not yet in that category. The hydraulic or mechanical driver that applies the compressive force still contains moving parts and therefore inherits some of the long-term durability burden that the nitinol itself has largely escaped. Generating the hard statistical data that proves survival across a full 10 to 15 year service life under real household conditions, with full warranty exposure attached, still takes calendar years. You cannot simply accelerate a decade of mechanical cycles in a laboratory without changing the very conditions you are trying to test. And the incumbent vapor compression technology is genuinely excellent at what it does. It has benefited from a century and a half of relentless industrial optimization, enormous global manufacturing scale, and continuous cost reduction. Beating those systems on paper inside a research laboratory is one significant achievement. Beating them on total cost per unit of cooling delivered on a high-volume factory line aimed at ordinary consumers is the real and still unfinished contest. None of those remaining challenges erases the fundamental advance that has already occurred. A 50-year materials wall that had stopped the entire field came down because a research team stopped pulling on the metal and started squeezing it instead. That is what most genuine technological breakthroughs actually look like in practice. Not the sudden discovery of an entirely new law of physics, but a change in direction or method that finally makes an old and well-understood law usable in the real world. Every major technology you rely on today passed through this exact awkward intermediate stage. The first electronic computers filled entire rooms and cost fortunes that only governments and large corporations could afford. The first practical solar cells were an expensive luxury developed for the space program. In each case, manufacturing scale, materials refinement, and accumulated engineering experience eventually transformed the economics. The historical pattern is consistent. A new approach works in the laboratory and looks impossibly expensive or fragile, and then, over time, it does not. Sit with the historical symmetry of the story for a moment. An American inventor working in Massachusetts in the 1830s created the machine that turned artificial cold into a practical utility for ordinary people. An American Navy laboratory in Maryland in 1959 accidentally created the metal alloy that might one day replace that machine. And a university research team located only a short distance from that same laboratory later discovered that the one direction of mechanical force almost no one had systematically explored, pure compression rather than tension, was the missing key that unlocked practical durability. One day in the not-too-distant future, you may open a refrigerator door and hear nothing at all. No compressor hum, no sudden late-night click as the pump starts up. Just a quiet, solid box that stays reliably cold because a carefully engineered piece of metal inside it is being gently squeezed and released over and over again, remembering its original shape and absorbing heat in the process. That leaves a practical and interesting question worth discussing openly. The familiar compressor is not only inside the refrigerator in your kitchen, it is also inside the air conditioning system of your car, in the ceiling units of your office or classroom, and in the large chillers of the commercial building down the street. If elasticaloric technology eventually reaches true commercial scale, which of those everyday applications is most likely to go silent first? And which of those familiar sounds will people notice missing the most when it is finally gone? Leave your thoughts in the comments below. And if you want more carefully researched deep dives into the technologies that are quietly reshaping the infrastructure of ordinary life, hit the like button, subscribe to the channel, and turn on notifications so the next story reaches you as soon as it is published.